Welcome. This talk introduces passenger car equivalents for their use in computing the heavy vehicle factor. The context is the highway capacity manual method for analyzing basic freeway segments and the underlying concept of equivalent base conditions. The first thing to know is that there are various conditions that influence highway capacities and service levels. There are roadway conditions, like the number of lanes, lane width, and shoulder width. There are traffic conditions, like vehicle mix and driver behavior. And there are control conditions, like the type of control device or the signal timing. Let's use this time here to understand how the presence of heavy vehicles affects the service flow rate of a basic freeway segment. We'll begin with key concepts, define some parameters, and finally, we'll prepare for basic freeway capacity analysis by computing the demand flow rate under equivalent base conditions, where the usual units of measure are passenger cars per hour per lane. Let's take a look at the basic freeway segment. We define a basic freeway segment as a segment of freeway outside the influence of merging, diverging, and weaving maneuvers. This is where the primary lane-changing behavior within the segment reflects only the normal desire of drivers to maintain their preferred speed, rather than changing lanes in order to exit or enter the facility. The most basic conditions under which the full capacity of the segment is achieved are the conditions of good weather and visibility, without work zones or incidents, and without serious pavement deterioration. These most basic conditions are assumed by the methodology. These conditions also include 0% heavy vehicles and a driver population composed of regular users of the freeway. There's also lane width and right shoulder clearances. These are base geometric conditions that are useful in estimating free flow speed. When actual field conditions differ from these base conditions, the analyst introduces the appropriate adjustments as given in the HCM methodology. We'll be giving particular attention to the adjustments that account for the presence of heavy vehicles, and then we'll turn our attention to the adjustment for driver population. The Highway Capacity Manual defines heavy vehicles as vehicles that have more than 4 tires on the ground. The HCM's greater than 4 tire definition captures some heavy-duty pickup trucks, like the one shown here in red that has 4 tires in the back and 2 tires in the front. The HCM explicitly identifies 3 classes of heavy vehicles: trucks, buses, and recreational vehicles, or RVs, but specifies just 2 types of vehicle parameters, one for trucks and buses, and one for RVs. This is because the operational characteristics of buses and trucks are found to be very, very similar. It has been observed that heavy vehicles affect traffic in 2 ways. One, they are larger than passenger cars and occupy more space. They also typically have poorer operating capabilities in terms of acceleration, deceleration, upgrades, and steeper downgrades. The term passenger car equivalent, PCE, represents the number of passenger cars that would use the same amount of highway capacity as the particular heavy vehicle being considered. On level terrain, a truck or bus may be equivalent to 1.5 passenger cars in terms of the impact on traffic flow. In rolling terrain, the same truck or bus may be equivalent to 2.5 passenger cars. The HCM defines the parameter E sub t as the passenger car equivalent of 1 truck or bus. When each truck or bus is equivalent to 1.5 passenger cars, we'd say E sub t equal to 1.5. The HCM defines the parameter E sub r as the passenger car equivalent of 1 RV. When each RV is equivalent to 1.2 passenger cars, we would say E sub r equal to 1.2. Note that the values in HCM Exhibit 11-10 apply only to extended terrain segments that can generally be classified as level or rolling or mountainous. There are separate tables in the HCM for specific upgrades longer than a half a mile and steeper than 2%, with values that range from 1.5 to 7 passenger car equivalents for trucks and buses, and a separate table with values that range from 1.2 to 6 passenger car equivalents for RVs. Here's a quick look at such a table. Discussion of this table is outside the scope of today's topic. Instead, let's take a moment to properly define level and rolling versus mountainous terrain. Level terrain is defined by any combination of grades that permits heavy vehicles to maintain the same speed as passenger cars, typically short grades of no more than 2%. A rolling terrain segment is any combination of grades that causes heavy vehicles to reduce their speed below passenger cars, but does not force heavy vehicles to operate at crawl speed. Mountainous terrain is any combination of grades that causes heavy vehicles to operate at crawl speed. Crawl speed is the maximum sustained speed achievable on an extended upgrade of a given percent. As shown here, for a 200 pound per horsepower truck on a continuous 4% upgrade, the maximum sustained speed after 7,500 feet is just about 32 miles per hour. Consider now a basic freeway segment on level terrain where the northbound demand volume for the study hour is 3,000 vehicles and includes 9% trucks, 3% buses, and 2% RVs. Given the level terrain, we would find E sub t equal to 1.5 for trucks and buses, and we would find E sub r equal to 1.2 for RVs. We also find that the HCM defines the parameter P sub t as the proportion of trucks and buses in the traffic stream. If there are 9% trucks and 3% buses, we would say P sub t equal to 0.09 plus 0.03 equal to 0.12, or 12%. The HCM defines the parameter P sub r as the proportion of RVs in the traffic stream, and if there are 2% RVs, we would say P sub r equal to 0.02. Now let's compute the heavy vehicle adjustment factor as follows from the HCM equation 11-3 as a function of the proportion of trucks and buses, the proportion of RVs, the passenger car equivalent for one truck or bus, and the passenger car equivalent of one RV. With the proportions represented and the passenger car equivalent from the tabulated values, we would have the below expression, solving for F sub HV equal to 0.94. So, 0.94, well, so what? Well, so this does start to become meaningful when we return to the notion of base conditions and then discover how the heavy vehicle factor we computed can be used to adjust for the presence of trucks and buses and RVs. Recall, the base conditions include no heavy vehicles, a driver population composed primarily of regular users, and so on. Before we move forward with the heavy vehicle factor, let's take a step back to a previous topic and incorporate what we already know about peak hour factor. Recall that we were given a freeway segment to consider with a northbound demand volume of 3,000 vehicles in the study hour. We were not given a peak hour factor, but we might assume peak hour factor equal to 0.9, which, as we know from prior study, represents a modest amount of flow variability within the study hour. Recall that we divide the hourly volume, capital V, by the peak hour factor to solve for the peak flow rate, lowercase v. 3,000 divided by 0.9 gives us 3,333 vehicles per hour as our flow rate. Under base conditions of no heavy vehicles, we would be analyzing a flow rate of 3,333 vehicles per hour. But this traffic stream does contain heavy vehicles, and we know that each truck, each bus and RV is equal to more than one passenger car. Thus, we are already anticipating a demand flow rate greater than 3,333 passenger cars per hour. Yes? Well then, perhaps it seems intuitively pleasing that we incorporate the heavy vehicle factor, 0.94, in the same way we previously incorporated the peak hour factor, which is in the denominator, where we take 3,000 vehicles, divide by a peak hour factor of 0.9, divide by a heavy vehicle factor of 0.94, and solve for 3,546 passenger cars per hour, where the abbreviation for passenger cars per hour is PCPH. Now, if the northbound segment of interest were to have 3 lanes, then a demand volume of 3,000 vehicles with the given mix of trucks, buses, and RVs would be equivalent to a demand flow rate under vehicle base conditions of 1,183 passenger cars per hour per lane, abbreviated PCPHPL. However, if the northbound segment of interest were to have 2 lanes instead of 3, then that same demand volume of 3,000 mixed vehicles would be equivalent to a substantially higher demand flow rate, equal to 1,773 when we take the 3,000 vehicles, divide by the peak hour factor, n equals 2 lanes, and a heavy vehicle factor of 0.94. Now that the concept of a heavy vehicle factor adjustment is reasonably clear, it is well and good that we introduce the HCM parameter V sub P, which is defined as the demand flow rate under equivalent base conditions measured in units of passenger cars per hour per lane. This demand flow rate represents the hourly volume adjusted for peak hour factor, the number of lanes, the heavy vehicle factor, and the driver population factor. Notice that this equation is mostly the same representation featured previously, where the one exception is the adjustment factor for unfamiliar driver populations, F sub P. Recall the concept of base conditions, which also included the condition of a driver population composed of regular users of the freeway. This is because it is generally accepted that traffic streams with recreational drivers use freeways less efficiently than do regular commuters. The adjustment factor F sub P is used in the denominator to reflect the effect of driver population. The usual values of F sub P range from 0.85 to 1, and unless there is sufficient evidence to the contrary, the analyst should use a value of 1, which reflects commuters or otherwise well-accustomed drivers. So if we were to return to the case of 3,000 vehicles in 2 northbound lanes and adopt the default value for F sub P, we would compute V sub P by dividing the demand volume of 3,000 vehicles by a 0.9 peak hour factor, n equals 2 lanes, a 0.94 heavy vehicle factor, and a 1.0 driver population factor, and find that the demand flow rate under equivalent base conditions is 1,773 passenger cars per hour per lane. So, that's all there is to taking an hourly volume and adjusting for driver population and the presence of heavy vehicles, along with peak hour factor and the number of lanes. If we had a suitable value for the segment's free flow speed, we could use our adjusted flow rate, V sub P, to proceed with estimating the level of service for a basic freeway segment. But that is a topic for another time.